let's just clear up this example exercise here. Now, how can we find now the distribution function of this random variable, which is now defined as the minimum of these two random variables, right? You can naively start in the same way. There is nothing wrong with it, but then you come across a slight problem. We can deal with actually along the line. Maybe I should again follow the same line of argument. So part B, right? So we are now interested in the cumulative distribution function of random variable u, namely the probability that u is less than or equal to a given number small u, denoted by smaller u, right? Again, you plug in the definition of random variable u, which is defined, right, as the minimum of random variables x and y less than or equal to u, right? Now you think again, right, before you worry about the probability, you ask to yourself, okay, what happens to random variables x and y if their minimum is less than u, right? So there is this label u. The smaller of them is below there. But does it say anything about what happens to other random variable? Well, it can be above or below. It really doesn't give much information, right? So you cannot right away apply this thing, but what you know, or when you think along these lines, you will just tell to yourself, right? Okay, if I knew that the minimum is greater than something, then I would conclude that both of them are going to be larger than whatever that lower bound is, right? Here I don't see that. This is like an upper bound, but then changing, right, the direction of inequalities is possible as you work with the probabilities. All you need to do is to look at the complement of this event. First of all, the probability of this event is 1 minus the probability of its complement. And what is the complement of this event? Now, minimum of xy is greater than u. Right? Now, I can handle this a lot better. Right? Since the smaller of x and y is larger than u, right? What is the conclusion? What can you say about each individual random variables here? The smaller is, right? The smaller of x and y is bigger than u. Huh? Both of them are larger than you. So this event is the same as saying that x is greater than you and y is greater than you, right? Since the events are the same, therefore the probabilities are going to be the same as well. So this is 1 minus the probability that x is greater than you and y is greater than you, right? And then, as before, we can use independence, right? Since x and y are independent, right? This is 1 minus the probability that x is greater than u times the probability that y is greater than u, right? I use independence to write this joint probability as the product of marginal probabilities, right? And what is this? This is 1 minus the probability that x is less than or equal to u, and this has this special name, right? That's the cumulative distribution function of random variable x, right? Therefore, I wanted to rearrange this thing. Otherwise, well, this can also serve as a final answer, right? And we can just write this entire thing as 1 minus the probability that y is less than or equal to u, right? Like this. And we know that this is fy, the cumulative distribution function of random variable y, evaluated at u as well, right? So finally you have what? 1 minus fx at u times 1 minus fy at the same u, right? And we can just open this, so develop this product here, right? So you get 1 minus fx of u minus fy of u, and minus plus fx u times fy at u, right? And this one again cancels one outside, and this minus will just, right, minus 1 multiplied with others will give you, first of all, fx at u plus fy at u minus the product of fx at u and fy at u. Okay? Alright. So this also gives you an idea about how you can manipulate different functions of random variables in order to find cumulative distribution functions, right? No questions, right? Okay. So another example. So this is a problem coming from your textbook, I guess on page 22. Your textbook has exercises and problems. Problems, I think, have answers at the back of the book that are designed for you to study on your own, so that you can check the results at the end of the book. Problems do not have answers in the book, so we'll probably pick up assignments from there for grading. But occasionally I will also assign exercises just to make sure that you actually visit and think about them, even though answers are behind the book, right? So I'm not interested in what you write on your paper, but I would like to just make sure that you actually take a look at those questions. Some of them are really important. All right, this is one of those problems. And it reads like this. A population having n distinct elements is sampled with replacement. All right? So a population like our class, right? It's just a general number n, and somebody comes in and just pick one person each time. After inspects him or her, just puts him back in the class or her into class, right? And because of the repetitions, right? So this is going to be repeated several times, and each time, since we are actually sending the person inside the classroom, next time, right, there is a possibility that we may actually pick the same person, call the same person outside, right? So because of that repetitions, right, those repetitions, a random sample of size R may contain fewer than R distinct elements, right? And let S sub R be the sample size necessary to get R distinct elements, right? So until you meet R distinct people, right? So you will have to call S sub R people outside, which may be more than R, right? I may just come in and call at random 4 people, and 3 of them may be the same person, and at the end of the day I will have known actually only 2 of you, right? And now the question is what? Okay, we would like to know on average how many times we should, or I should call somebody outside until I get to know R distinct different people from classroom. All right? So you may ask actually, why is this question interesting, right? So I guess biologists are facing problems of this kind. So you may actually, biologists, for example, if they go to a new jungle or just discover a new lake, for example, a lake full of fish, and they may just want to know how many different species live in that fish, in that lake, right? So they will just catch one, study that fish, and of course they will return it. So if you kill all of them, then there's no point of really studying all of them, right? They will not exist anymore. So, so fish, you cannot control. They are just actually swimming in this lake. So, how much time do you think, on average, a biologist actually spend on that lake until, let's say, they discover 10 new species, right? So they can actually use that time to estimate how many more species there might be in the lake, the ones that they haven't seen yet, right? There are models of this kind. So this is just a very simple version of that. So you assume that there is a large population, there are n distinct elements somewhere. You get a sample, study that individual, right? Take a note whether this is a person or a person individual that you have seen before or not, right? And then you return him or her back, and then you sample one more time. You may or may not come across with the same person, right? So how many times you should sample from the lake until you get R distinct species or individuals? Okay, yes?
In our case, in a class, we know the sample size, but in a lake, we don't know how many.
Sample size, you mean how many distinct people there are in the classroom? That's true, that's true. You have to start from somewhere. In that model, I didn't tell you all the stories. So this is also a parameter you have to estimate, and you also put it into estimation procedure. Right? But in this case, we'll just assume that we know what that is. Right? You can study later, for example, if you have a rough idea about what that is. Does it really change the result too much? If it is insensitive to what the population size is going to be, maybe it is okay. Because there is no way to know that anyway. You have to estimate that. For classroom, yes, it's under our control. Yeah. We'll just live with the imperfection in this case, right? Okay, is the problem clear to everyone? Huh? Right? So we have, let me just take a short note again, right? We have a population, right, of indistinct, right, elements. That's how they formulate it. Okay. And we take samples, right, with replacement. And that's, okay, we will define by S sub r. So this is a random variable now, right? This is the number of, okay, let me just follow the statement here, the sample size necessary to get R distinct elements, right? Or maybe I should say necessary until we get R distinct, we get to introduce two R distinct elements, right? You may ask, for example, what the distribution function or probability mass function of this random variable is going to be. That's a lot more difficult than just finding the expected value, which is what we are going to look for this example. On average, right, expected value, what is practical meaning of expected value of a random variable? On average, right, if you repeat this experiment on and on average, how many samples do you expect to get from this population until you really meet R distinct individuals, right? And your book is very kind. They actually provide the formula. They say that this should be n times 1 over n plus 1 over n minus 1 and so on till 1 over n minus r plus 1, right? And our job is just to justify, right? Explain why this is correct, right? We don't need to know this, but I guess this is one way to make sure that students can actually check their answers, right? So this is actually the solution of this problem will just contain a little flavor of what we usually do when you deal with the stochastic processes as well. First of all, actually this is a sequential procedure, right? You take one sample, you study, you pull in, you continue. Yeah. When you think actually what happens through that procedure, it will greatly help the solution of the problem. So what happens? So you take how many samples do you need to take in order to meet the very first distinct person or individual? Huh? How many samples do I need to take in order to meet the very first distinct person? Yeah, it's as simple as it. Yeah, the question is so long, so you sometimes lose where this is going, right? So you take so let's say this is horizontal axis for sample size, right? What did I say? We don't know a priori how many samples I need to take. It can be arbitrarily large, right? So there is no end. So you start with one, it can go as far as an arbitrarily large number, right? And it is a random number. Each time you repeat this experiment, you will get a different number, but each one of them, in theory, right, or in practice even, can get arbitrarily large, because our luck may be so bad that we may come across the same person 10,000 times. And although the probability is small, it still has a positive probability. But what I know is, when I get the first sample, that's gonna be the first distinct person that I see. Now, how many more samples do you need to take in order to meet the second distinct person? A person that you have not met before. As small as one, right? Can it be two? Of course. If you just happen to pick the person that you have just met in the first trial, right? Now you have to take another sample, right? And wait to see whether you will meet a second one or not. So let me make this a big bar. So then there will be a bunch of small bars. I don't know how many, but it's a random variable itself, right? Till you get the second distinct person, right? So that's where you meet the first distinct person. Then you have these small bars. Who are they? Well, this is the same person as the one that you have seen, right? Therefore small. So I don't really pay attention. Therefore I make it. So you met the first person, you meet him several times until you get another person for the first time. So this is when you get the second distinct person or element, whatever, right? Right? Then, now your job is even more difficult, because now you know you have already met two people, and when you sample one more time here, now you may actually pick one of them, right? And that is going to happen perhaps several more times, and they don't have to be the same, right? It may just take even longer or shorter. Who are they? These are either this person or that person. I don't know who. But there will be a time, eventually I'll just meet a person different than the first and second. This is exactly when, this is the sample, when I get to know the third, right? Distinct person, right? Then maybe the fourth one is just right the next one, right? It's random. So as before, it can take as small as just taking one sample until you meet the next new person, right? Or not. So this is, what is this picture that I am drawing? This is what we call is just a realization of the stochastic process, right? So next time, if you just draw this, you may have actually, or repeat this experiment, you may actually get a different picture. Maybe you will have only one, and then second here, so two, then the third, then a long delay, and this. This can happen, right? What I am really paying attention here, or I would like to pay attention, is the procedure itself. I'm trying to identify the random variables associated with this process, not the exact values themselves, right? So now you have a better picture, right, in your mind, what is going on. Now, I still have to find, right, the expected value of this random variable. By the way, where is that? Where is this random variable? This is the third. You just proceed until you meet the odd person, right? So let me just break this line, right? So it goes like this for a while. There will be R minus first distinct person. This is going to be the sample on which you will have met the R minus first. And you will wait some more time, and finally you will have met the rth distinct person, right? Distinct person. So, counting from 1 till here, this will give you SR. This is exactly SR, right? So, sample size necessary until you get the R distinct element. But the picture now helps me see the following combination. Okay, SR is actually sum of simpler random variables. What are they? So we can call, right, there is this x1. Maybe I should call x2 actually. let me call x1 or denote by x1 the number of samples I need to take until I meet the first distinct person. Let me call or denote by x2 the number of samples I need to take or number of additional, right? Additional, in addition to what I have taken before, until I get the second distinct, I get to meet the second distinct person. And similarly, let's denote by x3 the additional, right? Additional number of samples on top of what I have observed before, additional samples until I get the third distinct person, and it goes like this, right? Finally, this is XR. So let's just introduce this carefully. So XK, let me just define this as the additional number of samples needed, right, until kth distinct, right, person is met after, right, k minus first distinct person was found, right? The xk is somewhere in between, right? Now, if I define it like this, then SR is what? It is the sum of x1, x2, and xr. Right? When we start discussing, for example, queuing systems, or these are like waiting times for us. So a customer arrives, some number of unit measured as time or some other, in terms of other measurement unit, right? You have to wait this many units until a new event happens, and the next important event will happen only after x3 units of time, or whatever the unit is, will pass, and you are interested in the total number of units pass until the R of them happens, right? So I have something like this, right? And then, since now the original random variable, right? Since I was interested in the expected value of that random variable, and since it is the sum of random variables, it is again, its expectation again is the sum of expectations of these elementary random variables. Are they really elementary? We'll see that they indeed are, in the sense that it is much easier to calculate their expectations than the expectation of SR. Right? And let's take, well, the first one is obviously very easy to calculate, x1. We said x1 itself is always equals 1, therefore its expectation is 1. So we know what this says. Right? So what happens to this one, x2? Well, in fact, we don't have to worry about the second one. We can just look at, for any arbitrary but fixed k, right? xk. What is the expected value of xk? Right? We can even actually identify the probability distribution function of random variable xk. So xk is like what? So it's going to be somewhere here, right? So let me just take that part. So you have just met the R minus first distinct person. Now you are actually counting, right? You took one sample, you have taken one sample, you have taken another, till you meet the rth distinct person, right? And why is R? So I should have called K, right? I'm interested in xk, right? So the number of samples you have taken here equals exactly, or be denoted by xk, right? Now if you have taken probability course, perhaps you remember what kind of a random variable xk could be. What kind of a random variable xk? What does it do? Huh? Uniform? Okay, we are in the same class, but not exactly. That is not exactly what I was looking for. Why is uniform?
We can
I guess xk is somehow something to do with the experiments, Bernoulli experiments. You repeat, right? You fail, and that will be the first one you succeed. Huh? Normal? Definitely not, because normal distribution is continuously distributed random variables. The probability that a normal random variable equals something like 14 always equals 0. This takes integer values anyway, right? It is not normal. We'll see. I'll remind you what normal was, right? But does that statement ring any bell in your mind? So there are these you repeat the Bernoulli experiment. Bernoulli means what? So every time you conduct an experiment, right? You will either see it fails, or binomial random variable does what? Counts. It counts the total number of successes, right? So Bernoulli is used to basically label whether it is a success or failure, right? And we discussed it, right? The success probability. Binomial, if you repeat independent identically distributed, or if you repeat experiments whose outcomes are independent identically distributed Bernoulli random variables, right? So that's binomial, right? So you count total number of successes, right? And there was also what? The time needed, or number of times you need to repeat the experiment until you get the very first success. Poisson? No. Geometric, yes. But names are not that important. It is more important like when I describe, like okay, you repeat an experiment and you wait until you get the first success. That's what I want, right? So you should be able to, derive at least its probability distribution, even though you don't remember what the particular name or label for the distribution is. Yes, well, xk is one of them, right? So here you repeat you conduct an experiment. What is the experiment? I call somebody outside, right? And I look at the person, and you know that I cannot really remember the names very well, but let's say I must have done my job, right? My homework, and I can tell whether this is a success or failure. Success, it is a success if the person I just called outside is a person that I haven't met before, right? And it is a failure if I have already met a person, because then I need to repeat the experiment, right? So then, and this is indeed the time when I get the first success, when I get a new person, right? When I get to know, get introduced to a new person, right? When I call somebody outside, right? So xk is, and the experiments are independent of each other. The results on each experiment is independent, and they are all identically distributed. Why? Because first of all, when I call somebody outside, right? After I get a conversation with that person, I send him back. So just before the next experiment, if I have to ever take that experiment again, I have exactly the same statistical distribution inside the classroom, right? So nobody left the classroom, right? I did not send add another person inside the classroom, and I am still also selecting people completely at random, right? So all these experiments are actually statistically identical, and they all have the same success probability, right? So what is that success probability? xk. First, we now agreed that xk has a geometric distribution. Right? Now we have to identify the success probability with success probability. When do we have a success? It's a success, we get a success. Excuse me. It's a success, right? Okay, it's a lot. Okay. You get a success if if we meet a person for the first time, right? So when does that happen? What is the probability of that? 1 over n?
1 over n minus k plus 1.
Let me see. Which one is it? 1 over n is one possibility. How would you argue? Which one is going to go first? Why is 1 over n? Why do you think it is 1 over n?
It's first success, so probability of success is 1 over n.
Say it again. Probability of successes. It is.
I thought that you are looking for the first success, so.
You mean the first example until you get the. Well, let me see.
X1.
We know what x1 is. What was x1?
First.
It's the number of people number of samples until we get the very first distinct person. But we said this is 1 already. Right? Maybe you are thinking like x2. What is the distribution of x2? Or, well, okay, it's a geometric distribution. What is the success probability for x2?
1 over n minus 1.
Okay, 1 over n minus 1. Why is that?
Because we have already to choose someone.
Right.
Are we separating the chosen ones from the
Okay.
remaining set?
Okay. Yes, okay. Right, so for x2 it is like this, since we have already actually met one person, next time, right, x2 is exactly the additional number of samples until we get a second distinct person, right? And it will take, let's say, x2 will equal 1, 2, 3, 4, 5, 6, 7, right? Only when the first 6 people, right, in the first 6 trial, I must have met the same person, right? And that will happen with probability 1. On the first trial, it is going to happen with probability, I must have selected person, that particular person, out of how many possibilities? When? Huh? I started to confuse myself as well. Okay. Okay. That's true. This is true, right? Huh? So there are n people. So I'll call somebody outside. And it's going to be a failure for me if I happen to call a person that I have met, the only person that I have met by that far. With probability 1 over n, it's going to be a failure for me, right? So for x2, right? So x2 equals k. No, I use k. Let me use another letter. What is it? What is your favorite letter? Let me use j, right? So I need j additional samples until I meet the second distinct person, right? This probability equals to what? With probability 1 over n, I must have chosen the same person that I have met before, j minus 1 times, and on the j trial, with probability 1 minus 1 over n, or if you wish, this is like the n minus 1 over n, because any one of the remaining n minus 1 person is new to me, right? And with this probability, I will meet one of them, right? So the success probability is then what? Success happens with this probability, right? So then x2 has geometric distribution with success probability. Sometimes people use p, 1 minus 1 over n, right? Is this clear? Huh? Do you agree with me? Now just apply the same thinking for the kth one, right? So we have already met k minus 1 people in the past. Now I am repeating the same experiment, right, until I get to know the kth distinct person, right? So it's gonna be a failure if I meet, right, on any one of these examples, any one of the k minus 1 people that I met in the past, right? That's a failure for me, right? So we can just again calculate the probability that xk equals j, right? So j can be, of course, any number as small as 1 or arbitrarily large, right? Okay, what is this probability? So this means that in the first j minus 1 trials, right, I must have actually failed to meet a new person, and the total number of people that I have already met is k minus 1, and out of n people, right, on any example experiment, right, I'll just fail to meet a new person with this probability, and this will repeat itself j minus 1 times, right? And finally, with probability 1 minus k minus 1 over n, I will meet a new person, a person that I have not met before, right? And that's going to give me the probability that xk, right, the total number of samples till I meet the k person equals exactly j. And this is again the success probability for this geometric distribution, right? So the conclusion is what? Our conclusion is what? All these random variables, right? x1, x2, and so on, right? All x till xr, right? These are all geometric random variables, right? And they are also independent of each other, but they are not identically distributed. Their success probabilities are different because life gets a lot difficult, right? As I progress, it will take on average more time till I meet a new person. That is reflected in the success probability of the corresponding random variables geometric distribution, and we can just summarize it here, right? This thing equals now k minus 1 over n to the power j times n minus k plus 1 over n, right? So that is exactly 1 minus the failure probability, right? Okay, and but I'm interested in, okay, I know more than what I really need, right? I need to know the expected value of xk, right? Because when I get there, then I'll just sum them up, right, here to solve the problem. And intuitively, what is this? We can actually just drive it using the formula, but for a geometric random variable, let me just take x, right, without any index, just a generic one. So let's say this is a geometric distribution. This is a random variable geometric distribution with success probability p, right? So for example, p equals 1 over 5, right? Okay, let me give a numeric example. What does this mean? This is success probability. That means in every 5 trials, I get 1 success, right? 1 in 5, right? So on average, you are just making 5 tries before you get the success here, right? It's not like, of course, it's a random variable, but the meaning that you can give on this thing. So the expected value of x is going to be what? Yes, it is like what? A number of samples you need until you get the first success. And this says basically you have to wait on average 5 tries until you get the first success. This is like 5, right? 5 is like what? 1 over p. Okay. Right? If I put here, of course, 0.49 and so on, it is a lot difficult to argue, but it's the basic idea is the same. All right? But if you really want to absolutely be sure why that this is the case, then you would just take what? You can just do this calculation, right? X times the probability that random variable x takes this value, it is 1 minus p to the power x minus 1 times p. This is one way to solve. You have to calculate this thing, and it is not my favorite. I'm not going to do that, right? Maybe later I can show you that there is an easier way to do that, right? So this is also true. The probability that x is greater, but expected value of x is the same as the expected, or the sum of the tails of probability mass functions. The probability that random variable x is at least as large as small x, alright? And this is like the x or more, this is like the 1 minus p to the power x minus 1, which immediately give you a geometric series for which we know the answer and so on and so forth, right? That's just a hint for future. When we have an exercise where we need this one more time, then I'll just try that, right? So intuitively at least, right, as we have just done here, this is going to be just what? 1 over the success probability, right? So, okay, and the success probability for xk was this, and 1 over this is going to be n over n minus k plus 1, right? So this is true for every k, even for k equals 1. Because when k equals 1, right, this just cancels, n over n gives you 1. Right? So we said x1 is identically equal 1 all the time. And of course, the expectation will also be the same as the random variable, the value the random variable takes. Right? So this is 1. If you wish, well, okay, I didn't pay attention that we use actually capital N, but we can fix that problem by just changing this to smaller, right? That's easier. Okay, so 1 is the same as n over n, right? Plus, what is this now? According to that formula, instead of k you will put 2, right? So in the denominator you have n minus 2 plus 1 or n minus 1, right? N over n minus 1. And as k grows, the numerator is going to get smaller, right? So this is n minus 2. And finally, n over n minus, for k equal r, you get this, right? So n is common to all of them, you get exactly this. If I also just correct this formula for my mistake, right? This is how you get it. So what did we learn from this exercise? It is not important whether we have an expression or not, but you have a sequential procedure. Sometimes it is important to just go through how this procedure actually unfolds over time and identify simpler random variables in terms of which you can write these more complex random variables in a easier way, right? Since it is a lot easier to calculate the distributions of these individual blocks, right, building blocks for this random variable, at least when it comes to calculate only expectation, for which I only need to calculate expectations of the simpler random variables and then sum them up. Right? But if you ask what the distribution of SR is, it is still a difficult problem. But I guess this will still give you an easier way to deal with that problem. SR is the distribution, so it is like, okay, the distribution of SR is going to be the convolution of the distributions of all these random variables, right? What is that? It is just actually you are basically summing up probability distributions after you multiply them along an appropriate division among all these random variables. Right? That doesn't help anyway. So I guess this just illustrates the main point that trying to find simpler ways to express the harder, complicated random variables. All right. Do we have any questions about this problem exercise? Okay. We can. Okay. Let me give a short break again before I look at the distributions. Now, in the last hour, I'll just quickly summarize this well-known distribution. We talked a little about Bernoulli, right? We reminded ourselves what a binomial was. I'll just do it again, right? Then we'll just remind ourselves what the Poisson distribution looks like. Then I'll mention how Poisson and binomial distributions are related to each other. Have you ever heard this law of rare events in your probability course? We'll quickly look at that because that also is going to give a clue about the Poisson processes that we will spend a lot of time to discuss, to learn, and to model, for example, all these service systems. Service systems are typically modeled with Poisson process. The customers arriving to a restaurant, for example, they follow a Poisson process with such and such arrival rate. Right? Okay. Okay, I'll see you in 10 minutes.